Assalamualaikum and a very good day. My name is Muhammad Afif bin Rodadi. My matrix number is 231543160. And today I'll be presenting my problem-based learning individual project report, as you can see on the poster provided. My focus is on topic 8, which explores the critical engineering domain of the Energy Storage Management System, or ESMS. The global automotive industry is currently undergoing a massive and rapid shift toward electric vehicles, commonly known as EVs. Because of the transition, our reliance on lithium-ion batteries has grown exponentially. However, the physical realities of battery chemistry present significant engineering hurdles that must be overcome to ensure sustainability and safety. This presentation will guide us through the core problems facing EV batteries today, current technological standards, a real-world case study, and my proposed AI-enhanced solution to maximize battery efficiency. Let's begin by looking at section 1, problem identification. A modern EV battery pack is not a single unit. Rather, it consists of thousands of individual lithium-ion cells. A critical issue the industry currently faces is the degradation, thermal instability, and inefficient energy distribution within these complex battery packs. Why does this happen? Due to manufacturing tolerances and varying temperature distributions across the pack, these thousands of cells do not operate identically. They age, charge, and discharge at completely different rates. Without precise intervention, this creates a severe imbalance. In any battery pack, the weaker cell dictates and limits the total capacity of the entire system. This issue is of paramount importance because battery degradation directly and negatively impacts an EV's driving range, its overall lifespan, and the total cost of ownership for the consumer. Furthermore, poor thermal management can lead to localized hotspot left unchecked. This can trigger a thermal runaway, a catastrophic and highly dangerous chain reaction that causes battery fires. Therefore, a robust energy storage management system is absolutely essential. We need it to maximize energy efficiency, ensure the utmost passenger safety, and accelerate consumer trust in emerging EV technologies. Moving to section 2, let's review the technology involved in a standard ESMS. An ESMS often encompasses a battery management system, or BMS. It is highly complex architecture comprising sensors, microcontrollers, and specialized software algorithms. There are three core technologies at play here. First, cell balancing circuit. To fix the imbalance I mentioned earlier, system use either passive or active balancing. Passive balancing simply bleeds the excess energy from highly charged cells, releasing it as heat. Active balancing is far more advanced. It uses DC to DC converters to actively redistribute energy from the stronger cells directly to the weaker ones. Second, state estimation algorithms. The system must dynamically estimate the state of charge, or SOC, and the state of health, or SOH, of the battery. This is achieved using advanced mathematical models such as column counting and extended Kalman filters. Third, thermal management integration. The ESMS continuously reads data from thermistors placed across the battery modules. Based on real-time readings, it controls liquid cooling pumps and fans to ensure the cells remain strictly within their optimum operating temperature window, which is between 20 degrees Celsius and 40 degrees Celsius. High-end EVs today typically utilize distributed topologies using a CAN bus network to allow a master controller to communicate with multiple slave board monitoring the cells. To ground this in reality, let us examine section 3, which details a highly successful international case study, Tesla's integrated battery management system. Tesla vehicles, particularly the Model 3 and Model Y, utilize a proprietary distributed BMS architecture to manage thousands of their 21700 or 4680 cylindrical lithium-ion cells. A defining engineering feature of Tesla's implementation is how their ESMS integrates with a patented liquid cooling ribbon that physically snakes between the individual cells. The master controller continuously monitors cell voltage and temperature. If the vehicle is plugged into a supercharger and the system detects high heat, the ESMS actively and proactively ramps up the liquid cooling flow. The outcomes of this approach are highly impressive. Because of this precise management, Tesla batteries exhibit industry-leading longevity. Real-world data demonstrates a degradation of only around 10 to 12%, even after completing 200,000 miles of driving. Furthermore, Tesla utilizes over-the-air or OTA software updates. This allows them to continuously refine their ESMS algorithms based on fleet data, improving safety and range retroactively without needing a change to physical hardware. This brings us to section 4, the core of my project, the proposed solution. While current systems like Tesla's are highly effective, they primarily operate on localized, rule-based algorithms. They react to heat after it occurs. My conceptual idea is an AI-enhanced cloud-connected ESMS. This proposed system integrates traditional local safety controls with advanced cloud-based machine learning. The goal is to optimize battery life predictively rather than just reactively. The conceptual framework works on 4 levels. Number 1, edge computing. The local vehicle retains full control over immediate safety parameters like voltage limits and emergency thermal runaway prevention, utilizing standard CAN bus architecture. Number 2, an IoT gateway streams telemetry data such as state of charge, ambient temperature, and internal resistance patterns directly to a secure cloud platform. Number 3, the cloud AI engine. This is the core innovation. The AI module analyzes the vehicle's historical data alongside external factors like route topography and live weather data. For instance, if your navigation is set to mountains region, the cloud AI will send a predictive profile to the local ESMS. The vehicle will pre-cool the battery in anticipation of high discharge climbing it is about to do, drastically reducing thermal shock. Number 4, adaptive charging. Instead of always fast charge at maximum capacity, the ESMS syncs with the driver's smartphone schedule. If it sees that the car will not be needed for 12 hours, it lowers the charge rate to preserve the internal cell chemistry. As detailed in section 5, the multi-sectoral impacts of this proposed AI-enhanced system are profound. From an economic perspective, significantly extending the battery lifespan delays the need for extremely costly replacements, which often exceed $10,000. It also increases the vehicle's secondary resale value. From an environmental standpoint, lithium-ion battery production is heavily resource-intensive, requiring the mining of cobalt, lithium, and nickel. Extending lifespan directly reduces battery waste, lowers the carbon footprint, and lessens the ecological disruption of the EV life cycle. Socially, providing a predictive, highly visible system reduces range anxiety and improves user confidence, accelerating our transition to zero-to-emission transportation. My primary project objectives found in section 6 are to design this comprehensive system architecture designed to the key data parameter required for predictive thermal management and theoretically evaluate the potential percentage increase in battery cycle life compared to standard rule-based system. To achieve these objectives, section 7 outlines my systematic engineering methodology. The approach consists of 4 steps. First, conducting a thorough literature review of existing state of charge algorithms. Second, modeling the system architecture to map the communication flow between the IoT gateway and the cloud server. Third, developing the AI algorithm by formulating logic parameters based on inputs like driver habits and elevation data. Finally, conducting simulation and analysis. I will utilize MATLAB and Simulink to model a battery pack undergoing standard drive cycles, specifically the WLTP, to compare heat generation and stress with and without my predictive thermal management system. As shown in section 8, this comprehensive project plan spans a standard 14-week academic semester, moving from topic selection in week 1 through architecture design and culminating in the final review and e-learning submission by the due date of June 26, 2026. Thank you very much for your time and attention today. I hope this presentation has clearly outlined the vital importance of evolving our energy storage management systems to ensure a more efficient and sustainable automotive future. Assalamualaikum. Until next time.